Hello, guys, and welcome to Maths and Science 8. As promised, in today's live, we'll be going through calculus, specifically optimization problems. And obviously, as per the previous videos, this will be based on previous exam papers. So, to get things started, I would like for us to start with this one. So I think this is quite a very interesting question. It is from the DBE May-June 2022 exam. So I just also included here, the first calculus question, determining f prime of x from the first principles, as well as these questions here, which require you to differentiate using the rules of differentiation. But obviously, these are basically free marks, guys. I hope that we are all confident with this. Otherwise, if you do need help with this, you can let me know in the comment section below. But specifically, I want us to be focusing on the optimization problems. But this one, it's quite a unique question because they combined the optimization problem, under this cubic polynomial question here in question 9. As you can see, 9.4 says determine the maximum vertical distance between the graphs of f and f prime in the interval from -1 up to 0. So between this interval in the values of x. So I found this to be quite interesting. So before we get here, let us just quickly go through these questions about this cubic polynomial as well, because they are quite important too. Okay, so this now will be kind of a follow-up to the previous live session that we did, whereby we're going through functions. So we're also going through, the cubic polynomial, which is also part of calculus. So anyway, here sketched below is the graph of f of x equals to x cubed plus ax squared plus bx plus c. So you'll notice that, they like doing this. They like giving you an equation of a cubic polynomial that is incomplete. And as expected, the first question here is asking us to show that this is the complete equation of f. Okay, but before we get into that, we can see that the information we are given is that the x-intercepts of f are at 3 and 0. So it's this x-intercept as indicated in the graph, excuse me. And also at m, so m is another x-intercept here. And as we can see, excuse me, m lies on the negative x-axis, right? And then we're also given k with coordinates 0 and -3, which is the y-intercept of f. And then we're also told here that m and n are the turning points of f. So this is quite interesting now, specifically with regards to point m. Point m is not only the x-intercept, but it is also the turning point of this cubic polynomial. So that is very, very important to note. It's very, very key. And for those who have actually watched the very previous live session, you'll actually recall that there was a question similar to this that we did there. And similar to that question, the first problem was to show that, or to kind of work out the unknown values, in the equation of that cubic polynomial, which is what we need to do for 9.1 here as well. So here is the thing. This is how we can work this out. And let me be honest and say this, you know, usually if you are given a problem like this one, for me the very first thing that comes to mind is that I will try to substitute in the coordinates that I have into the equation and then try to solve the equations simultaneously. But in this case, we do not have enough information to do that because we only have got 2 points. We know this point, the x-intercept, so obviously the coordinates here are 3 and 0, and we also know the y-intercept, that is point K. So we only know 2 points here, and that is not enough for us to solve this simultaneously. But here's the key thing. The key thing lies with M. Since M is a turning point and also the x-intercept. So if we are looking at this, it seems like we only have two x-intercepts, but this is a cubic polynomial. Why is that the case? So whenever you've got a cubic polynomial and you only have got two x-intercepts, it means that the factors for your cubic polynomial are as follows. Firstly, in this case specifically, we can say that the first factor will be x minus 3, because we know that one of the x-intercepts is at x is equal to 3. So it means that the factor must be x minus 3. So you change the sign for that x value, because it means that now we can solve this for x, by making f of x equal to 0, and then it would be x is equal to 3. That's how we get this x-intercept. And then what about point M here? So let's call this xm, okay? So regarding that, since now that is the only other x-intercept we have here, it means that we actually have x plus, I'll just say plus, oh, actually, it should be minus. Oh, yes, it should be plus. Yeah, it should be plus. We'll say plus xm here. Xm, because obviously you can see that xm is on the negative. It lies on the negative x-axis, as we were told, or as we can see on the graph. So that factor here would be x plus xm. But of course, we do not know the value of xm, so that's why you are doing this. Now, here's what you need to keep in mind. Since, again, this is both a turning point and an x-intercept, and since here you see that we only have 3 and m as our x-intercepts, it means that this x plus xm here must be a perfect square, because normally in a cubic polynomial you should get 3 x-intercepts. But this simply means that in this case, two of those x-intercepts are the same, they are equal. So actually, this is similar to, just quickly, let me show you this. This is similar to when you've got a quadratic equation, a quadratic function with a turning point as an x, as an x-intercept. So, okay, let me do this. I want to clearly show that this is, yeah, there we go. This is our turning point. So this is similar to if, for an example, you've got a quadratic function like this one. Let's just say it's g, and let's say that maybe this is 2. If you've got something like this, it means that the equation for your quadratic function, obviously, it would be a into x minus 2 all squared, right? It would be all squared. It would be a perfect square like this, simply because you see that we only have a single root here, or a single x-intercept. But technically, there is not a single x-intercept here. You do have two x-intercepts, but they are equal. Hence, in using the language of the nature of roots, we would say that we've got real but equal roots in this case. So it's a similar thing with with this kind of a cubic polynomial. So keep this in mind whenever you come across a cubic polynomial like this one, whereby one of the turning points is also an x-intercept. it means that the factors, for that for the equation of that cubic function will be like this. Okay, so that's the key thing to solving this question. And you do not have to worry about the value of a, and I'm referring to the coefficient of x cubed. As you can see, the coefficient of x cubed here is 1. So it means that our a, besides this, the a that is given as an unknown here, I mean, it's causing a bit of confusion, because normally we write the general equation in this way, as ax cubed plus bx squared plus cx plus d. So now I'm talking about this value of a. So in this case, this value of a is 1, meaning that here you do not have to worry about that, because if we did not know that, we're gonna include it here as an unknown, but we can already see that it is equal to 1. So that is already sorted out. Now, the next thing that we need to do after this is we can now take the point K and sub it in here, and then solve for the value of xm. So if we sub in point K, we are gonna get -3 equals to 0 minus 3 into 0 plus xm. So we have just simply substituted in the x value as well as the y value of point K into this equation. So f of x will be -3 because that's the y value, and x will be 0. And then our only unknown is xm, which is very amazing. And just note that you cannot use point the x-intercept here. You cannot use the x-intercept, because if you use the x-intercept, then this equation will be 0. So you need to use point K specifically. And then we just simply need to solve this. So we'll have -3 equals to -3. 0 minus 3 is -3 into xm. Well, in fact, this will just be x squared m. And then, as you can see, we can divide by -3 on both sides of the equation, and overall we'll get that x squared m equals to 1. And then we can apply a square root on both sides of the equation here, meaning that xm is equal to plus or minus 1. Remember that it should be plus or minus 1, because this equation here that we are solving is basically a quadratic equation. Or alternatively, we could have solved this as follows. We could have taken this +1 into the left-hand side, and then you can see that you've got a difference of 2 squares here. So you can factorize. This will be xm plus 1, xm minus 1. So we have got two values of x, plus or minus 1, okay? That's important. But obviously, we can see that the value of xm that we are looking for here, firstly, here on the graph, xm will be -1. So it will be -1 because it's on the negative x-axis. However, here on our f of x that we are solving, that must be positive. So we'll have f of x equals to x minus 3 into x plus 1 all squared, which is why here we've got our x-intercepts at x is equal to 3, which is the one that we're already given, and we also have the x-intercept at x is equal to -1. That's what we are going to get, from this perfect square factor here. Okay, but of course that's not what we are trying to do here. We are trying to work out the equation of f of x, and now to do that we simply need to expand this equation. So we must start by expanding this perfect square. So the shortcut of doing that, you just simply need to square the first term. So that will give us x squared. And then for the middle term here, we will multiply x by 1 So x multiplied by 1 is x, and then we multiply that by 2. So x multiplied by 2 is 2x. And then what is 1 squared? 1 squared is 1. So that's how you can quickly do that. And then we need to expand these two brackets. So x into x squared, that's x cubed, x into 2x, that's 2x squared, and then x into 1, that's x. Negative 3 multiplied by x squared, that's negative 3x squared. Negative 3 multiplied by 2, that's negative 6x. And then, yeah, negative 3 multiplied by 2x, and then negative 3 multiplied by 1, which is negative 3. We just need to add up any like terms that we have. So we have got 2x minus 3x squared. That will give us negative x squared. And then we have plus x minus 6x, which is negative 5x minus 3. So there we have it. As you can see, the equation that we have obtained is exactly the same, as the equation that we're trying to prove. So that's how you can do 9.1. Refer to the previous video if you want to see, this a similar question to this one. If you hadn't watched that already. And now the second question here, 9.2, is simply requiring us to calculate the coordinates of n, which is the second turning point of this cubic polynomial. So right now we do know the complete equation for f of x. So we know that to find the turning point, we need to work out the derivative of f. So this will be 3x squared minus 2x minus 5. And then at the turning points, we know that the first derivative is 0. And that's because the turning points are also known as stationary points, because at the turning points, the gradient is 0. So that's why we can do this. And then from here on, we can just, solve for x here. So we can use the quadratic formula. I'm not gonna write it down. I'm sure we all know how to do that. But I suspect that we might need this answer. So let us calculate it. I'll just, show the calculation. But remember that in the exam, it is important for you to write the formula down and show your substitution. So minus into negative b, minus b, and our b is negative 2 plus square root of b squared. So that will be negative 2 squared minus 4, a is 3, and c is negative 5, divided by 2 into a. So we have 5 over 3, x equals to 5 over 3, or x equals to, so let's just change that positive to a negative and see what we get. As you can see, we get negative 1. So this makes sense because it's now also, giving us confirmation, regarding what we said about m. We had already identified that the x value of point m is negative 1. So this negative 1 here refers, to this turning point. And now for n, as we can see, we would expect this to be positive. So the x value of the turning point of m is 5 over 3. Now we just need to work out the corresponding y value. So in order to find that, obviously, we need to sub in 5 over 3 into the original equation. So 5 over 3 cubed minus 5 over 3 squared minus 5 into 5 over 3 minus 3. So we need to punch this into our calculator. Okay, so let's do that. So we've got 5 divided by 3 cubed minus 5 divided by 3. Oops, we need to square this one, so I need brackets here. So we square this and then we minus 5 into 5 over 3, and then we just subtract 3. So the y value, yeah, I think let's just write this one as a decimal, negative 9,48. Negative 9,48. Therefore, the coordinates for n are 5 over 2 and negative 9,48. So there we have it. And now let's move on to 9.3. 9.3 says, for which values of x will f of x be less than 0? And as you can see, that's only for 2 marks. So you just need to refer to your graph. We want to know the values of x where f of x is less than 0. As I usually say, whenever you come across a question like this, you just need to understand that f of x simply stands for the values of y in the graph, right? So firstly, we need to identify here where are our y values on f negative, and then identify those values of x which corresponds, to those y values. So it's very simple. F of x is less than 0. Graphically, it means that you need to look into your graph where it is below the x-axis, because less than 0 means negative. So the y values of f will be negative below the x-axis. So for an example here, as you can see, this part of the graph is below the x-axis. This is also below the x-axis, up until you reach x is equal to 3. You see? But now you need to be careful about point M and this x-intercept here, because at point M, f of x is not less than 0, but it is equal to 0. The value of y here at point M is 0. And likewise, the value of y at x is equal to 3 is also 0. So those shouldn't be included in your solution. Otherwise, you'll simply write your solution as follows. We can say that for all those values of x that are less than m, or if I were to draw a vertical line exactly at point M, you will see that, so this vertical line is going through point M, which has an x value equal to -1. On the left-hand side of this line, our graph is below the x-axis. So the first part of our solution is x is less than -1, the x value of point M. And then you also see that on the right hand side of M, still our graph is below the x-axis. However, this happens up until we reach x is equal to 3. So our second part of our solution will be as follows. So our second values of x are in between -1, right? The -1 of point M, all the way up to +3. So this is exactly, guys, how you can work out or solve a problem like this. So this will be our solution. And obviously, you can also write this using the set notation. And just to discuss this a bit more, as you can see now, after x is equal to 3, f of x is above the x-axis. So the y values are now greater than 0. Or in other words, here on this portion, f of x is greater than 0. It's no longer less than 0. So that's why that is not going to be part of our solution. Otherwise, this is the answer to 9.3.1. And you can also write this using the set notation as x is an element from -infinity up to -1, union from -1 up to 3. Okay, and then 9.3.2 is another interesting question here. We need to determine whether for which values of x will f be increasing. Will f be increasing? It's very straightforward. I mean, you can immediately say that. Firstly, note what I was saying regarding the turning points. I mentioned that the turning points are sometimes referred to as stationary points because at the turning points, the gradient is 0. So it means that at the turning point, a function is neither increasing nor decreasing. It's just stationary. However, in this case, we see that on the left-hand side of the turning point of m, this function is actually increasing, because if you were to calculate the average gradient, you will see that it will be a positive gradient. Likewise, on the right-hand side of point n, you can again see that our graph is increasing. Again, you can simply estimate that or determine it by, you know, calculating an average gradient. However, now between point M and point N, as you can see, our function is actually decreasing. Now you see it's sloping downwards, but obviously we are focused, or we need to determine where it is increasing. So it's a very straightforward thing. 9.3.2, the solution here will be x must be less than -1 firstly. Again, as you can see on the left hand side of point M, if the values of x are less than that, they are less than the x value of point M, then the function is increasing. And then it also increases when x is greater than what? Than the x value of the turning point of n. So x must be greater than 5/3. You see? So that is as simple as it is, guys, to do this, to determine where a function is increasing or decreasing. You just need to know where your turning points are, or the x values of your turning points, and then you'll be able to see from your graph immediately whether, on which, intervals is it increasing or decreasing. And then we have 9.3.3. Here we need to determine the values of x where f will be concave up. Well, for this one, we do need to do a bit of a calculation. So, as you know, for concavity, we need to work out the second derivative, because if a function is concave up, then it means that the second derivative should be greater than 0, guys. So we need to solve this inequality. So here's our first derivative, as you can see. So let's work out from it the second derivative. So that will be 6x minus 2. So we need to solve this inequality. Let's just take -2 to the right-hand side, and then let's divide by 6 on both sides of the equation. So we will have 1/3. So it means that x must be greater than 1/3 in order for f to be concave upwards. If we wanted to know where this is concave downwards, then our inequality here was going to be less than 0. Okay? And then finally, we now get, to this optimization problem. So it's just a single question, one sentence, 6 marks. Determine the maximum vertical distance. That's the key thing. We want the maximum vertical distance between the graphs of f and f prime in the interval from -1 up to 0. Okay, so what is it that we are optimizing here? That's what you need to ask yourself or determine as you are reading, the statement. So we are trying to optimize the vertical distance. We want its maximum, right? If this vertical distance is between the graphs of f and f prime. So this is actually not, a difficult question at all. And as I usually say, the key thing is that if you need, for an example, to determine um, the length of a vertical line or simply a vertical distance on a graph, it's very easy because you do not necessarily need to use, the actual distance formula. You can just work out the difference between the y values, of those points. Similarly, if you want to work out a distance of a horizontal line, it's easy because you can just work out the difference between the x values, of the endpoints of that line. But it's important to keep in mind that a distance must be positive. So here, just to kind of visualize this, I'll try to, you know, to basically draft. Oh no, my calculator has been on this whole time. Sorry about that, guys, because I suppose that it did hide my writing as I was explaining. So let me quickly get back to this. Oh, damn it. I hate that. So what was happening here, in case you did not see as I was explaining, let me say, I think there's a comment here. What is it saying? Oh, okay. Okay, it has got nothing to do with what we are talking about here. So, okay, guys, I don't know if you saw this as I was explaining, but yeah, at least I hope that you heard what I was saying. So, this is what I had written down. I hope you can see, you know, just combine what I've written down here with what I was saying. And so with regards to 9.3.2, we wanted to know where F is increasing. So you saw as I was explaining that. So yeah, this is the answer to 9.3.2. And then for 9.3.3, we wanted to know where this is concave up. So we just solved this inequality. Maybe my calculator was hiding as I was writing this, but anyway, I don't think it's a big deal because yeah, it's easy to follow, right? Apologies for that. Now, back to our question. So right now, what I want us to do, I just want us to quickly draft how the graph of f prime of x would look like. And here's what you need to know for that. We know that at the turning point, right, we find the x values of the turning point by setting the first derivative to 0. So it means that if you were to take this first derivative as its own function, just forget that this is a derivative. Imagine that we just had, a function of x given by this equation, and then we make f of x equal to 0. What do we call the values of x that we get here? X-intercepts, right? So these values of x here at x is equal to 5 over 3 and x equals to -1, these are going to be actually the x-intercepts for the graph of the first derivative. So our first derivative will have an x-intercept there and an x-intercept here, because again we say that this is our equation for the first derivative and we equated it to 0. Okay, and now the next thing that you need to take note of is that actually the point of inflection which we get from the second derivative, in this case, it would be x is equal to 1 over 3. So just imagine that this wasn't an inequality, but it was just an equal sign. So it means that this 1 over 3 is obviously our point of inflection. You see, we get the point of inflection by deriving the first derivative and then equate that to 0. So again, imagine that this was its own function. We had a function, maybe, let's say it was g of x equal to this. F prime prime of x here was going to be g prime of x. And then if we take this g prime of x and equate it to 0, it means that we are setting the first derivative of g to 0. And whenever we are doing that, as you know, it means that we are working out the turning point of g. So the point, the point that I'm making here is that this point of inflection, which is at x is equal to 1 over 3, is the same as the x value of the turning point of f prime of x. So if you want the graph for f prime of x, it will have a turning point at 1 over 3. So 1 over 3 would be, for an example, approximately here, 1 over 3. And then if you want to know the corresponding y value for this point, you would have to sub in into f prime of x. But we don't have to worry about that. Let's just say that maybe it's around here. Let's just estimate it. So now this is what I'm trying to achieve here. I just want a quick sketch. Hey, this doesn't look like a nice curve. I think I can do better than that. Yeah, I think that's better. So you see what we have here in red is just, a sketch for f prime of x. And now back to the question quickly. So we need to determine, the maximum vertical distance in the interval from -1 to 0. So from -1 to 0. So imagine that we've got a vertical line because here is -1. Remember that -1 is here, right here, right? It's the x value of m. So 0 is obviously here. So this vertical line, we can say maybe here it is, but we want it to be a maximum. So obviously the distance of this line will just be a difference between the y values of these 2 points. The point that is above is on f. So our vertical distance, let me write here. The vertical distance is going to be given by the y value of f. We must write down the y value of f, but we do not know it. But obviously the y value of x can be obtained from f of x as long as we know the x value. And then we'll have to subtract the y value of the point below, which is on f prime of x. So we need to subtract f prime of x. You see, that's how you are gonna work out your equation. And then we know the complete equation for f. I'm gonna substitute it in here, right? And we'll do the same thing for f of x, f prime of x. Here is the equation for f prime of x. And so note here, the reason that I even wanted us to draft this so that you can have a picture is because as you are, setting this equation up, it's important that you subtract, the y value, you subtract the smaller y value from the bigger y value. So this point is above, f of x is above here, and f prime of x is below. That's why you must do the subtraction in this way to ensure that you get a positive answer. And let us not forget that this should be inside brackets. So, okay, I'm gonna fix this now. Let me just quickly move it to down here. To down here, okay. So yeah, basically, this is the equation that you'll have to construct, right? And then after this, it's easy, guys. You'll obviously have to expand here. So you'll have the vertical distance as a function of x. So you'll expand here. You have you'll have x cubed minus x squared minus 5x minus 3. And then this will be minus 3x squared plus 2x plus 5. And then you need to add up the like terms. And then, as you know, with optimization problems, you then need to work out the first derivative. So you need to add up all the like terms here and then find the first derivative. And then you set that equation to 0 to find your x values. So you'll get two values of x after doing that, but you are given here the interval. So you'll only take the value of x that is within this interval. And then after getting that value of x, whatever it is, I'll just say x is equal to a, the one that is within this interval. You'll obviously then just sub in it into the original equation for the vertical distance. And then that will give you the maximum vertical distance. So I won't be able to do all of this with you because I need to quickly rush, into a meeting that I have, a tutoring meeting with one of my students. Otherwise, later on, I will be live again. So make sure that you are subscribed and your notifications are turned on because there's still more questions here that I want us to do. Here are some of them. So yeah, there are many interesting questions, guys, but like I said, I am now rushing because I'm a bit late for this session. So yeah, there are many interesting things to look at. So later on, once I am done with my meeting, I'll be back, guys, and we'll be going through all of these questions. So yeah, for now, that is it from me. See you later on. Good luck.